This is a video about the 2025 Nobel Prize in Physics, and the reason why you should watch this video in particular is simple. Because there is a story here. The bare facts are quite banal. John Clark, Michel Devoret and John Martinez have been awarded the 2025 Nobel Prize in Physics for discovering, or rather demonstrating, macroscopic quantum mechanical tunneling. Okay, that's quite a mouthful, and of course we're gonna talk about what it means in a bit. But there is more to this. There is a why, there is a what, there is a how. Why were they even interested in this in the first place? What did they attempt to achieve? And how did they do it? Physics isn't just numbers and variables and weird diagrams, because all of these things have a meaning and a connection and a history. And this is the story I will tell in this video, starting with why. We need to start way back in the 1920s and 1930s, the very dawn of quantum physics. This new theory had just ushered in the greatest revolution in physics since Isaac Newton and had finally explained all, or let's say most of, the weird behavior of atoms, radioactivity, photons, etc. At this point it was already obvious that quantum mechanics was an excellent description of the world of atoms and other small particles, called the microscopic world. However, it was quite unclear how quantum mechanics can be reconciled with our macroscopic world, the world of humans and cars and houses, or cats. The question was very much, why don't we see any of those quantum effects in the everyday world around us? Why is there a separation between microscopic and macroscopic? And where exactly is the dividing line? The most famous example for this dilemma was Schrödinger's cat. A thought experiment by Erwin Schrödinger. He was one of the founders of quantum mechanics, but he later became one of its fiercest critics. Schrödinger's idea was to combine a quantum system, a single atom, with a macroscopic system, a Geiger counter, poison and a cat in a box. These components were arranged in such a way that if the atom decays, the Geiger counter would detect this and release the poison and kill the cat. Unnecessarily cruel, yes, but it is what it is. The point was to create a scenario where an event in a quantum system, the atom decaying, would trigger an event in the macroscopic world, the cat dying. And this could be used to transfer quantum effects to macroscopic objects. For example, as soon as the atom enters a combination of quantum states, decayed and not decayed, this would also leave the cat in a combination of being poisoned and being alive. And to Schrödinger this was obvious nonsense, because such half-dead, half-alive cats simply do not exist. And that was his entire point, that we do not understand the transition from quantum physics to the macroscopic world. Obviously, atoms and electrons are obeying quantum rules, but can everyday macroscopic objects, like a cat, also show some kind of quantum behavior? Can you interfere cats or entangle them or tunnel them? How big can quantum systems get? One of the most mysterious of those new quantum effects was the so-called tunnel effect, or quantum tunneling. It was discovered very shortly after the birth of quantum mechanics, and it's actually just based on a wave phenomenon we already know from optics. Basically, when a wave enters an obstacle it has insufficient energy to cross, what happens is that the wave declines exponentially. This means it quickly drops towards zero. And while technically it never quite becomes zero, for all practical purposes, it very soon is. Now, if the width of the obstacle is small enough, this reduced wave may still have some appreciable size when it leaves the obstacle on the other side. So it comes out very much diminished, but not zero. In optics, when a light wave manages to tunnel over a small gap of air from one glass prism to another, you can see it as a faint beam of light. In quantum mechanics, the wave function decides the probability of where you can find a particle. So, if the wave function can tunnel through barriers, the associated particles can do that too. The most striking example of quantum tunneling was described by George Gamow in 1928. Alpha particles in an atomic nucleus can tunnel through the force barrier holding them inside, which is the explanation behind alpha radiation, a common form of radioactivity. Without quantum tunneling, this would not exist. But can macroscopic objects also do this? Can a cat simply pass through a wall? I certainly wouldn't try that at home. While all of this talk about macroscopic quantum effects was very much relegated to thought experiments in the 1930s, this changed in the 1950s and 1960s, when superconductors became ever better understood and more widely available. What's a superconductor? Well, it turns out that some materials lose all of their electrical resistance below a certain temperature. Yes, that means an electric current can flow through them without loss. The catch is, this certain temperature is extremely close to absolute zero. So around minus 270 degrees Celsius or minus 450 Fahrenheit. There are also some interesting magnetic effects in superconductors, but we'll not talk about those today. What materials exactly are superconducting? Well, for example, mercury or lead or aluminium or some alloys like niobium, titanium. And the most modern compounds look something like that. Not gonna pronounce that. In a superconductor below critical temperature, pairs of electrons can combine into Cooper pairs. And all Cooper pairs in a circuit can combine together into a condensate and essentially become a single quantum object. Oversimplified, you could say that they all do the same thing. Please note, this is an illustration used in the official Nobel Prize announcement. There was no way I was not going to use that here. Anyway, we have billions or even trillions of Cooper pairs together in the same collective state. And the collective properties of this state cause macroscopic effects in the circuit that we can directly measure, like current or voltage. And this is exactly where the Nobel laureates come in. In 1985, Clark, Duvoré and Martinez constructed a superconducting circuit where the condensate was oscillating in a trapped state. In terms of energy, it was in a so-called tilted washboard potential, because that's what it looks like. And just like the alpha particles in the nucleus, the system can tunnel out of this potential. Even though in this case, it doesn't mean leaving a place, it means leaving a state. It means changing from the trapped oscillating state to a state where the condensate is circulating. And that's exactly what the laureates could demonstrate. One remarkable detail of the experiment was that this change of quantum states was directly measurable as a voltage in the circuit. It switched from zero voltage in the oscillating state to non-zero in the running state. And measuring voltage in a circuit is very macroscopic. It's a very basic thing. This is what the Nobel Prize was awarded for, the definitive proof of a macroscopic quantum state tunneling. And with that, we've gone through the why, what and how of this year's Nobel Prize. But that still leaves one question open. First up, maybe you're a bit disappointed that Schrödinger was talking about cats and all we got was a lousy supercurrent. Yeah, you know. In quantum terms, having trillions of particles is extremely impressive and a huge step towards the scale of everyday objects. And if you say, well, that's just a bunch of electrons, yeah, true, but a cat is also just a bunch of atoms in the end. So anyway, the domain between micro and macro systems is still of intense interest, so this will not have been the last experiment in this direction. And the next logical question is, of course, yeah, that's all cool and interesting in principle, but can we use it for something? Yes, very much. Firstly, this kind of superconducting circuits are the basis for squids, which are ultra-sensitive measuring devices that can be used, for example, for medical or for geophysical use. They have also been extensively used in our search for dark matter particles, for example. Also, this experiment was in many ways a prototype for superconducting quantum computers. And I will do a short about this soon-ish. Let's see. I am Chris and this is Physics But Awesome. If you liked this video, subscribe for more.